You wowie.
Mario Party. It's a series that's known for both bringing friends together as well as making new enemies. The concept of having a game be divided into a whole bunch of smaller mini-games is a brilliant idea, but having all of those mini-games be tied together to the main game mode being a board game, that's just genius. Especially since the minigames add an element of skill to a board game that's mostly luck-based on its own, since winning the minigames awards you coins, and coins are what's needed to buy stars, with the winner being the player who has the most stars at the end of the game. Not only can coins buy stars, it can also buy items, which add another layer of strategy behind the whole game, with the item's usefulness depending on the scenario that the player just so happens to be in. Especially since the newest entry in the series, Super Mario Party Jamboree, has a wide array of items for the players to obtain. Such items include the skeleton key, which can be used to open gates to access new parts of the board that originally couldn't be reached before, or the custom dice block, which lets the player bypass the RNG entirely and choose how many spaces they want to move. There are also some items that let the player troll other players, like the creepy dice block, which lets the player choose someone to only roll 1 to 3 on their next turn, or the swap mirror, which lets the player swap spaces with a random opponent. But the items I want to talk about today are the double dice and the triple dice, and they function exactly as you think they would do, with the items letting you roll multiple dice blocks instead of only one. Valuable if the player wants to cover a lot of distance. But the catch is, that distance isn't guaranteed since there's a probability that the player can roll low across multiple dice blocks. But how likely, which is why in this video I'm going to be listing all of the mathematical probabilities of rolling each number with what type of dice block. Especially since Super Mario Party Jamboree introduced a new item exclusive to the Roll 'em Raceway board called the Turbo Dice, which lets the player roll 4 dice blocks at once at the expense of passing all board events, such as the item shops, the boo, and even the star space, which makes it a very risky item. So hopefully you can use this video as helpful advice for knowing the probabilities of you possibly passing the star. Without further ado, let's dive right into it. Let's start with the probability of the double dice item because you don't actually have an equal chance of rolling any number from 2 to 20. And I'm going to be using 2 standard 6-sided dice as an example. For those who have played craps at the casino, the most likely number to be rolled in that game is 7. All of the other numbers aren't that close in probability either, as you are 6 times more likely to roll a 7 with 2 6-sided dice than you are a 2 or a 12. 3 times more likely to roll a 7 than a 3 or 11, and twice as likely to roll a 7 than a 4 or 10. To explain why that's the case, let's just say you rolled the 2 dice separately instead of simultaneously. If you are trying to get a 12, then the only way that would be possible for you is to roll a 6 on the first throw. Same with a 2, where you must roll a 1 in order to even have a chance of getting a 2. As for a 7, it really doesn't matter what number you roll on the first throw, as you will still be eligible to roll a 7 on the second throw. Knowing this is not only useful for craps, but it's also useful for any game that uses 2 6-sided dice to play. Another example would be in the board game Monopoly, where it is commonly believed that the orange properties are the most valuable to obtain due to the properties being within a 7-space distance from jail, which is one of the most commonly landed on spaces in the game. Now going back to the topic of Mario Party, where if you took that same logic with the 6-sided dice and applied it to Mario Party's 1 to 10 dice block, it's revealed that 11 is the most likely number to be rolled with the double dice item. And much like the 2 6-sided dice, the other numbers are pretty far apart in probability, as you are 10 times more likely to roll an 11 than a 2 or 20, 5 times more likely to get an 11 than a 3 or 19, and twice as likely to get an 11 than a 6 or 16. Since rolling a 2 requires getting both 1s and a 20 requires getting both 10s, which for both is a 1 out of 100 or a 1% chance of those outcomes even happening. And I'm just going to say it right now, the dice block going up to 10 made it so much easier to get the exact probabilities because powers of 10 are by far the easiest of all number exponents. If you were trying to roll higher than a 10, the odds are slightly in your favor by a margin of 55 to 45. And if you wanted to go really far, then you have a 15% chance of rolling higher than a 15. But on the opposite end, you have a 15% chance of rolling less than a 7. Here's a chart with all the likely outcomes from the double dice and their respective probabilities. Now moving on to the triple dice, where measuring the exact probability starts to get a little more complicated. One silver lining is that powers of 10 are easy and 10 to the third power is 1,000, meaning all individual triple dice rolls are out of 1,000. Let's start off with the easy ones in that you have a 1 in 1,000 chance or a 0.1% chance of rolling either a 3 or a 30. Now moving on to 4 and 29, where there's only one likely scenario for both numbers. For a 4, you need to get a 2 and 2 1s, while you need to get a 9 and 2 10s for a 29. While it may seem like you have a 1 in 1,000 chance of getting either a 4 or a 29, keep in mind that these numbers can be arranged in a different order. An example being when getting a 4 with the triple dice, the 2 could either be the first number you roll, the second number you roll, or the last number you roll. Meaning if you were to get a 4, the outcome of the triple dice could either be 2-1-1, 1-2-1, or 1-1-2. Which would mean that there are 3 different outcomes of getting a 4, which would mean that you have a 0.3% chance of rolling a 4 with the triple dice. Same thing for the 29, where your dice block total could either be 9-10-10, 10-9-10, or 10-10-9. The same logic is used for the 5 and 28, but the main difference is there are now 2 different number combinations. For getting a 5, you could get either a 3 and 2 1s or 2 2s and a 1. Which means if you add the two 0.3% outcomes together, you have a 0.6% chance of rolling either a 5 or a 28. At around the 6 and 27 mark is where it starts to get a little more complicated. Because in order to get a 6 with the triple dice, you need to get either a 1, a 2, and a 3, a 4 and 2 1s, or 3 2s. And all 3 of these outcomes don't yield the same percentage. Because much like the triple 1s or triple 10s, that's only a 0.1% chance of getting either triple 2s or triple 9s. You have a 0.3% chance of getting a 4 and 2 1s depending on whether you roll the 4 first, second, or last. The 1, 2, 3 outcome is also the first time where all 3 numbers are different, which means that the order could either be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1, adding up to 6 different outcomes for a 0.6% chance. If you add the 0.1% from the triple 2s, the 0.3% from the 4 and 2 1s, and the 0.6% from the 1, 2, 3, you have a 1% chance of rolling either a 6 or 27. If you don't notice already, for every outcome where all 3 numbers are the same, add 0.1. For every outcome that has a pair of matching numbers, add 0.3. And for every outcome where all 3 numbers are different, add 0.6. So if you keep listing all of the possible outcomes for each number and adding the percentages up based on their respective number configuration, the percentages for rolling each number will eventually look something like this. How I know this is correct is because if you add the percentages up from 3 to 16 or down from 30 to 17, you will get 50% both ways, which, as you know, would total up to 100%. And if it wasn't obvious, the most likely numbers to be rolled with the triple dice are 16 and 17. As you are 75 times more likely to roll a 16 or 17 than a 3 or 30, 25 times more likely to roll a 16 or 17 than a 4 or 29, and 5 times more likely to roll a 16 or 17 than a 7 or 26. Here's a chart for all of the percentages. Now on to the item that made me want to make this video in the first place, the Turbo Dice. A new item introduced in Super Mario Party Jamboree that's exclusive to the Roll'em Raceway map, and it lets the player roll 4 dice blocks at once, but comes at the expense of bypassing all board events such as the item shops, the boo, and even the star space. which I think is brilliant because while you have the potential to get so much distance on the board, it's actually possible to overshoot it and miss the star entirely, which just adds an element of risk to it. Now on to the real question. What's the probability of getting each number? Well, since there are 4 dice blocks that go up to 10, each individual number combination is 1 out of 10 to the 4th power, or 10,000, or 0.01%. That 0.01% is the same percentage chance you have of rolling both a 4 and a 40, so the easy one is out of the way. Now moving to 5, where the only possible way to get that is a 2 and 3 ones, but the order could either be 2-1-1-1, 1-2-1-1, 1-1-2-1, or 1-1-1-2, which means you have a 0.04% chance of rolling either a 5 or a 39 with 3 10s and a 9. Now on to 6, where it can be obtained by either one of 2 ways, either a 3 and 3 ones or 2 2s and 2 1s. Much like the 3 of a kind for the 5 or 39, you have a 0.04% chance of rolling a 3 and 3 1s. Now the real question here is, how many different numerical configurations are there for rolling 2 pairs? If we talk it out, there's AABB, ABAB, ABBA, BBAA, BABA, and BAAB, which means there are 6 different configurations for 2 pairs, or 0.06. Which means if we add the 0.04 from the 3 of a kind and the 0.06 from the 2 pairs, the percentage chance of rolling a 6 or 38 is 0.1%. Things get even more complicated for 7, where not only are there 2 3 of a kinds in the form of a 4 and 3 1s and a 1 and 3 2s, but there is a new configuration in the form of only 1 pair. Now this leaves another question. How many different configurations are there for only 1 pair? But in order to find the answer to that, let's first find out how many different configurations there are where all 4 numbers are completely different. Because going back to the triple dice, there are 6 different ways to arrange 3 different variables. It should also be noted that 6 is 3 factorial, or 1 times 2 times 3. If factorials are applied for the 4 turbo dice, it's revealed that 4 factorial, or 1 times 2 times 3 times 4, is 24. With 24 representing the many different ways to arrange 4 different variables. Now for just 1 pair, simply divide that by 2 and it's revealed that there are 12 different ways to arrange 4 different variables with 1 pair. Why that's the case is because, let's say you wrote out the 24 different combinations of A, B, C, and D, and if you replaced all the D's with an extra A, that leaves you with 12 pairs of the same combinations. So to sum everything up, if there are 4 of the same number, add 0.01. If there are 3 of a kind, add 0.04. If there are 2 pairs, add 0.06. If there's only 1 pair, add 0.12. And if all 4 numbers are different, add 0.24. Meaning if you correctly write all possible numerical configurations for each total correctly and add them up correctly, these are what the final percentages look like. We see that the most likely number to be rolled with the turbo dice is 22, with a 6.7% chance of getting that total, which is 670 times more likely of getting that than a 4 or a 40. Another thing to add is that 11 is the most likely number to be rolled with the double dice, which is half the amount of the most probable outcome with the turbo dice. As for the triple dice, 11 plus 5.5 is 16.5. And what would you know? The most likely numbers to be rolled with the triple dice are 16 and 17. Which means for every 1 to 10 dice block that's added, the most likely number to be rolled goes up by 5.5. How I checked my work to make sure it was correct was with a dice probability calculator that I found online. And wish I know about sooner, to save me the time and headaches for trying to find this. Also, it should be noted that the Mario Wiki also has the total percentages for every number to be rolled with each type of multiple dice block. Just thought I'd mention that. How the calculator found those exact percentages was through a different method from what I initially used. It instead used this complex formula for finding the exact outcomes, with R representing the exact sum, N representing the number of dice rolled, and S representing the number of sides on said dice. I guess the way I did it is longer and more prone to making mistakes, so I learned something new from this experience as well. Anyways, I hope you found this to be interesting, and I will see you next time.